Have you ever just stopped to think about the sheer amount of digital stuff we create, like every single day? I mean, every click, every single post, every transaction, it all adds up to this mountain of data that's growing at a totally staggering rate. So let's dive right in, because it brings up a huge question. Where on earth do we put it all?
And when I say staggering, I am not kidding. We're talking 2.5 quintillion bytes of data every single day. For decades, the answer was pretty simple. We just file it all away neatly in what's called a relational database. Think of it like the world's most organized digital filing cabinet. Everything has its place in these nice, structured tables. But here's the thing. Those old filing cabinets, they were never, ever designed for this kind of daily data avalanche. They're starting to crack under the pressure.
All right, so before we can get to the solutions, we really have to wrap our heads around the problem. I mean, why are these traditional systems that have served us so well for so long, why are they suddenly failing under the sheer weight of all this data?
And this really gets to the heart of the issue with those traditional systems, the RDBMSs. See, they were built for order, for structure, for consistency. So to handle more data, your only option is to scale vertically. What does that mean? It means you have to go out and buy a bigger, faster, way more expensive server. It's like your filing cabinet is full, so you have to buy a massive custom-built one to replace it. It gets really costly fast. And even worse, they often rely on a single storage unit, which creates this massive single point of failure. If that one thing breaks, boom, everything goes down with it.
Okay, so the old workaround for this was something called sharding, but honestly, it was a messy manual nightmare. You can see from the steps here just how complicated it is. The application, your actual software, has to do all the heavy lifting. It has to act like a librarian, figuring out exactly which shard or piece of the database to write the data to. And then when you need to read data, oh man, the application has to run around to all the different shards, pull the bits and pieces it needs, and then staple them all back together. It's just so slow, so complex, it just can't keep up.
This whole breakdown basically forced engineers to go back to the drawing board. It was clear the old way wasn't working, and the very first step was to rethink the most fundamental piece of the puzzle, how we store files on the hard drive itself.
And that line of thinking led to something called distributed file systems, or DFS. The idea was actually pretty simple. What if, instead of one giant, expensive server, we just spread our files across a whole cluster of cheap, everyday computers? A DFS is schemaless, which is a fancy way of saying it doesn't care what kind of data you throw at it. It's amazing for storing absolutely massive files and then reading them from start to finish, like streaming a movie. But, and this is a big but, it's not a database. It's super clumsy with lots of little files, it's terrible if you need to jump to a specific spot in the data, and there's no way to search what's inside the files. So, a really good first step for sure, but it wasn't the final answer.
The real breakthrough, the one that changed everything, came from a totally new way of thinking. People realized it wasn't about trying to patch up the old model, it was about throwing it out and inventing entirely new ones. And that, my friends, was the start of the NoSQL revolution.
Now, the name NoSQL is a little misleading. It doesn't actually mean no to SQL. It really stands for not only SQL. And it's not one thing. It's a whole new family of databases, each one designed for the messy realities of big data. They scale out horizontally, meaning you just add more cheap computers. They can handle any kind of data you throw at them, and they prioritize being available. This is a huge shift. They follow a principle called BASE, which means they'd rather be online and available, even if the data is a little stale for a moment, and then catch up later. It's the opposite of the old ACID model, which demanded perfect consistency, even if it meant taking the system offline to guarantee it.
But here's the cool part. There isn't just one type of NoSQL database. There are several, each with its own specialty. Let's start with the simplest one, the key value store. And the absolute best way to think about this is like a high-tech coat check system. So with our coat check, this approach is just incredibly fast and simple. It's perfect for things like storing a user's shopping cart online. The value is the cart itself, and the database just sees it as a blob of data. It has no idea what's inside. This means you can't go to the database and say, hey, find me all the shopping carts that have a blue shirt in them. Nope. All you can do is give it the unique ticket, the key, and get the entire cart back.
Okay, so that limitation leads us directly to the next type, document stores. Think of this as a major upgrade to the key value system. The value isn't just an unknown blob anymore. Now it's a smart, self-describing document, usually in a format like JSON. The database can actually open it up, read it, and understand what's inside.
And this is a total game changer, because now you can query the contents. You can go to the database and say, find all the products that are blue and cost less than $50. This makes them absolutely perfect for things like product catalogs or content management, where every item might be a little bit different. The catch? They still aren't the best at handling really complex relationships between different documents.
All right, next up in our NoSQL tour, column family stores. My favorite way to think about these is like a super flexible, almost magical spreadsheet. You know how in a normal spreadsheet, every single row has to have the exact same columns? Well, forget that. Here, every single row can have its own totally unique set of columns.
Now, why is this useful? Well, it makes them insanely efficient for storing what we call wide or sparse data. Just imagine trying to log every single thing that happens on a huge website. A click event is different from a purchase event, right? They have different details. This kind of database is perfect because it only stores the data that actually exists for each event. It's a natural fit for analytics platforms and tracking data over time, anywhere you have tons of possible data points, but not every entry has all of them.
And finally, we've got a type of database that is completely different from all the others: graph databases. With these, the focus isn't really on the individual pieces of data. It's all about the connections, the relationships between them. The perfect analogy? It's a map of your social network.
In this world, you're a node. Your friends are also nodes. And the friendship between you, that's an edge, or a relationship. What makes graph databases so powerful is that they are built to zip across these edges at lightning speed. This makes them absolutely unbeatable for things like recommendation engines. You know, the whole people who bought this also bought that thing. Or for fraud detection, where you're basically looking for weird or suspicious patterns of connections.
Okay, so we've tackled the problems of structure and scale. That's huge. But what about pure, raw speed? What about velocity? Because sometimes even the fastest NoSQL database writing to a physical disk just isn't fast enough. So the next big evolution was to do something radical. Take the disk out of the equation entirely.
And the why behind this becomes crystal clear when you just look at the raw numbers. Reading a megabyte of data from a disk takes around 20 milliseconds. Okay, now reading that same megabyte from memory, from RAM, it's about 80 times faster. That's not a small improvement, it's a completely different universe of speed. And for applications that need instantaneous, real-time responses, well, this changes everything.
This need for speed led to the creation of what we call in-memory data grids, or IMDGs. So what is it? Well, essentially, it's a system that takes a cluster of computers and pools all of their RAM together into one giant shared memory space. It spreads the data across all that collective RAM, instead of across hard drives. You can think of it as a massive, distributed, super resilient cache that delivers just unbelievable speed for real-time apps.
Okay, but wait a second. If it's all in RAM, what happens if the power goes out? How do you save the data permanently? A really clever strategy for this is called write-behind caching. Let's just walk through it. First, your application writes data directly into that super fast in-memory grid. At the same time, that change gets put into a queue, and right away, your app gets the all-good confirmation. Then, quietly in the background, that queue trickles the changes down to the permanent on-disk storage. This brings back that idea of being eventually consistent. The whole system is optimized for lightning-fast writes, knowing the permanent storage will catch up in a moment.
So, wow, we've gone from these rigid, old-school filing cabinets to this whole new world of specialized, high-performance storage systems. The big question now is, how do we put all these different pieces together into a smart, modern data strategy?
Well, the answer is summed up by this really cool term you might hear thrown around, polyglot persistence. Now, polyglot is just a fancy word for speaking multiple languages, and that is exactly the core idea.
You see, that's precisely the philosophy today. The modern approach isn't about searching for one single perfect database that can do everything. That unicorn doesn't exist. It's about building a toolbox. A single, complex application might use a classic relational database for critical financial transactions, a document store for its flexible product catalog, a key value store for managing user sessions, and a graph database for its recommendation engine. At the end of the day, it's all about using the right tool for the right job. This whole journey, from that one rigid filing cabinet to the diverse toolbox we have today, is just an incredible story of evolution, and it's all been driven by the mind-boggling scale of our own data. But here's the thing, this journey is far from over, which leaves us with a final big question to think about. As our data gets even more massive, more interconnected, and more intelligent, what new tools will we have to invent for the toolbox of tomorrow?